Hi everybody, welcome back. This is chapter 6 of the Art of Software Security Assessment. This is one of two chapters on the C language. This one deals a lot with integers and integer operations, and the other chapter is chapter 8 in the book. So we'll be getting to that one later. What I'm not going to cover in the lecture are things that are going to complicate the lecture. I'm actually taking a bit approach to understanding the integer issues, and I'm trying to simplify things so it's easy for you to learn. Here's a list of some resources that I have found very helpful. I actually like this last resource here as well, Computer Systems. Robert Secord, he also discusses about different registers and how C programs can recognize overflows and a variety of other matters related to that. Oh, this is a robot from Lost in Space. Yes, he's going to tell us when there's overflow dangers. It's a show from the 70s. So before you can get into overflows, underflows, etc., you kind of have to understand what the data types are, their sizes, what numbers they represent. Boundary conditions discusses arithmetic operations and how that affects the result. This chapter is about 100 pages, and most of it is in type conversions in C and less so in vulnerabilities. But I am going to cover the first three sections today, and I think it's going to be enough. You'll be ready to quit. So I'll go over, do a recap next week and next cycle, cycle 4, and then we'll go into chapters 7 and 8, etc. So this is a definition of an object, talking about a storage region and the execution environment. And to make this as simple as possible, I'm only going to concentrate on these first few. A character is 8 bits, short is 32, and I'm just going to use an int as well as 32 bits. There's some examples I use that are just 8 bits, and like I said, I will keep things as easy as possible to get that gets across the point really well, and actually it's easier to see this way. So precision has to do with the number of value bits. And I actually hadn't really given this much thought, but in addition to value, you have padding bits as well. So, for example, let's see. Well, actually, this is sign bits here. So any negative number is going to have a 1 in the most significant bit location. And if a number has a 0 here, then it's going to be a positive integer. And this, of course, is for a signed, some sort of signed integer. And so you can see that the largest number here is 7, and the largest negative number, there's an asymmetry here. So padding bits are also used in integers, but they're not used in the calculations. And oh, okay, yeah. Actually, some of this does depend on the implementation. I'm trying to keep things fairly general, and I think everything that I have here is correct. But some of this is somewhat independent on or dependent on the implementation. So there's a couple things you want to look at or try to remember from this chart. Remember I said that the negative number here is -8 and this is 7. So the negative number is larger than the positive number. And so you see that again here. If we're looking at a 2's complement, so 2's complement is just a signed integer. And you can see that the positive numbers here are smaller than the negative numbers. And you might want to give that a little bit of thought, why that might be. The other thing to note here is when you go to unsigned, the FFFF is the largest integer, and it's also -1. So this is asking why is there an asymmetry. So when you're counting up the positive integers here, and I'm talking right now about the 2's complement, when you're talking about those, you start at 0 and you count up, right? 0 up to 7, that's your first 8 integers. When you start on the negative scale, you're really barring the 0. You can think of it this way, you're barring the 0 here, so you're really counting -1, 2, 3, 4, 5, 6, 7, and it goes up to -8. So this is really why there's an asymmetry there. And you can see, if you think about how would you convert an unsigned to a signed integer, this is also basically the way you do it. You would, if you had something like -2, if you had that as an answer, as a number, if you converted it into the unsigned number, it would be a very high number. Usually a very large number if you're using a lot of bits. So the other thing, and I pointed this out in the last slide, is that the positive numbers, they end right here. And so these positive numbers always have a 0 here. And once you get into the negative numbers, you always have a 1 in what is the most significant bit in the most significant bit. So this is actually just another, that's just another way of looking at the last chart. And it just kind of shows you the same information. So I did talk a little bit on one of those slides about converting from 2's complement, which would be unsigned. Which are signed, and then going to an unsigned answer here. So I wanted to show you how this is done, and I think this really does a good job of illustrating that. So the numbers that are positive here from the 2's complement, they go straight right here. And then the negative numbers, they actually go up here. They're the higher numbers, higher integer, well, higher, they're the larger integers. And if you think back on that scale, I had 15 that went from 0 to 15. At 15, it's -1. So that's basically why this happened. You start at, let's see, -8 and down to -1, and then you would put that up here. So that's how that works again. I think most people have a general sense of what an overflow is, but if the integer type cannot hold that many bits, then you have an overflow condition, or else you can also have an underflow situation. And this is just kind of a quick and dirty thing. This is kind of obvious how that works. The authors of the book said that this happens pretty often, and I was a little surprised to learn that. Okay, so we're going to talk a little bit about boundaries, and I said in the beginning that boundaries have to do with arithmetic, and so the arithmetic is subject to the rules of modular arithmetic. So this is similar to what you may have studied in cryptography with public key cryptography, RSA, for example, when you multiply P times Q to get the modulus, and you also use it in, I think, Euclidean and extended Euclidean. So it's used a lot in in cryptography, so I'm going to assume that you have at least some sort of understanding of it. And I'll give you an example here. So this is the modulus right here, and it's calculated by the number of bits that we're working with. So this is how you calculate it. It means that you divide 9 into 100 and you get a remainder 1. And so this really isn't a very good example. Let's say we had let's say we had a remainder of, no, actually we can use this one. So the highest possible value you can have for this one is going to be 9 minus 1, or 8. So it can go from anywhere between 0 and 8. This is one where you have an addition and the 1 is truncated on this. Lost in space. Okay, so these are a couple situations that you want to avoid. So in these, this one is actually making a table function, and it's trying to what am I saying about memory? It's trying to not designate, but it's trying to allocate memory by creating this table. And so when you multiply this, you get that number. And if you look at the modulus, again, we have 9 bits here, so it would be 2 to the 9. 2 to the 9 is, let's see, is it 256? I think it's 256 times 4. So that would be equal to 1024 bytes would be allocated in this table. Of course, the problem is that when you get into the for loop, it's going to use a height here, and the height for this is very high. It's a very high value. So it's going to be memory copying. It's going to be doing this, I think, somewhere around 16,000 or a little bit more. So that's the problem. The next one is also very similar to that. You're building, let's see, in 17, you're building a response array. And so you allocate the response array and then you fill it in with network data. If users can specify n response value that's large enough, you can they can cause a numeric overflow. And the result of the multiplication, again, would be a very small number because of the modular arithmetic. And you can just kind of think about the last example we use, where it's you end up with a small number that when you convert it, a small negative number, and then when you convert it, oh, actually, not necessarily a negative number, but a small number that when you convert it, it's equal to a larger number. So, and this actually came from OpenSSH. So you've probably heard a lot about SSL and OpenSSL most recently. Conversions are either explicit or implicit. I think everybody's pretty familiar with CAS when you do that as a programmer, and the implicit ones are a little bit harder to see and recognize and probably deal with. So some of the conversion rules deal with, or in some situations rather, there's value preserving. There's a value preserving answer, meaning that when you do the arithmetic, when you do the operation, you end up with a value that the integer type is capable of storing. Obviously, for something like this, where you have an 8-bit unsigned character, it's obviously going to fit into this one right here, which is an integer. It's a signed integer, so the 32-bit can represent any value of the 8-bit. So this would be one that's changing, because the unsigned you wouldn't be able to represent that in all positive numbers. Okay, so this just mentions of value preserving conversions. Let's see. Any notes? Let's see here. And I like this, the way he did this in the book. He talked about widening and narrowing. So it's just a little bit easier to talk about. So if you're going from a 1 byte to an integer, if the source is signed, the compiler uses a sign extension and propagates the sign bit. I showed that earlier with the ones are in the most significant bit, and the number will just have ones there. So, and narrowing, you get into some unhelpful situations like truncation. So let's see. Oh, okay. Yeah, actually, I wanted to mention this. This is actually a Greek letter, and I don't remember the name of it. But it actually is. It's equal to the number of bits. I think in my slides I may have used a W instead, but that's what this stands for. And this is actually when you're talking about padding. If the sign is a 1, or if the last and most significant bit is a 1, then you're going to pad it with 1s. And if it's a 0, you will pad it with zeros. And this kind of shows that. So if you have a 0 here, you're going to pad it with zeros. And F, of course, is 1, 1, 1, 1. So you're going to pad it with 1s here. This is kind of interesting because you have this is a signed char, and you're going to an unsigned integer. So it goes from a -5 up to almost the highest integer for that. And this is an example of going from something that's signed to unsigned. I showed you this a number of slides ago where the -1 was equal to 15 on the scale from 0 to 15. And that's kind of showing the same thing here. But you kind of have to get this in your head because that's what causes the problems with integers, or one of the problems. So in terms of truncating, you can get into situations like the second one here where you're changing the value pretty drastically. And that can lead to problems as well. So I think I showed you one of these charts earlier, but I like to do this when I'm trying to figure out what's happening with the bits when you're going either widening or narrowing. It's kind of helpful to think about where these bits go. And so the red and blue arrow, they would have to go up here. And so I will let you figure that out. It's actually it's the same as a lot of slides that I had. So let's see. The widening signed to unsigned, the value might change. Narrowing, we talked about truncation, and signed and unsigned, the bit pattern is the same, but the values change. So in terms of conversions, you can have a very simple one like a cast or assignment or a prototype, or you can have more complicated ones. I think I have one on assignments here. So if Mike is equal to a short and Roy is equal to an integer, you're setting Roy equal to a short integer. And let's see, we'll convert the int to the short int when you do the assignment. Prototypes are used quite a bit in C, and they tell the compiler the number of arguments that you have, as well as what types you're going to be using. This one we have 3 arguments, and we have an int and an unsigned char. Okay. Okay, let's see here. I'm going to actually skip this one for the moment. Integer promotions. This one is a little bit different in that this is dealing with smaller integers that are smaller types of C types that are smaller than an integer. And so we talked about a char, char, we talked about a short. So that's 8 bits and 16 bits. So what this is saying is when you have an arithmetic operation on something that's 8 or 16 bits, the integer types are promoted to the integer. So they're promoted to the 32 bits. And as an example here, let's take a look at this one. Since the operation precedence would start, well, we have parentheses down here to even make it simpler. So we're starting with 190 right here. And let's see. This is a char. So it is only, let's see, it's only 8. It's going to only be 8 bits, and since it is unsigned, it's going to be minus 148 up to 147. So at this point, you would have an overflow right here, just adding these first two numbers together. And so when you promote them to an integer, you don't have the overflow, and then they're converted back once they're done. So I'm running out of time, and I just wanted to say thank you for watching. I'm going to be talking about the rest of the vulnerabilities next time, and I'll have a little recap of what we did. Thanks for watching, and we're going to go on to chapters 7 and 8. This is the other chapter on C. It deals with strings and meta characters. And then once we get done with 7 and 8, and I know Chad is working on some of these as well, so I will obviously skip any material that he covers. But after that, there's Unix, and 2 chapters on Unix and 2 on Windows. And that goes through about 700 pages in the book, so it goes through quite a bit. And we'll see how far we get with this, but I'm going to try to get through Windows and Unix if I can. So see you next week. Bye.